All right, everyone, and welcome to week 54 of Chill Kernel Hacking for Fun. This week, we are continuing with Lab 5, which is the file system lab. Last time, we made a lot of good progress. We were working on, I believe, some of this core file system walking routines, and then starting on the file system server. And that is what we're going to continue with today. So let's just get into it. Let's take a quick look at the Git history just to remember where we were. And yes, I believe I had tried to do something, but it wasn't working. So let's see what that was. I think it was exercise 5 and 6 is what I was kind of scrambling to do last time. Let's check out exercise 5 and see if I did that. So serve read. So what's this file? Dev file, right, okay. I think this was maybe the unfinished part. Serve read. So what is serve read? Serve read is this function right here. So when a process wants to do file system activity, what it does is it uses an IPC channel to talk to the file system server. And serve read is the final part of this like IPC interface before it hits the core file system routines that are private within the file system server. And what does serve read look like? It's responsible for taking this IPC message that we received from the other environment via shared memory. And we use the information within the IPC request to complete the request. We get a bunch of information within the IPC message request. So we can look up a file ID. And then we can call the core file system function within the file system server to do the request. I think this line is not used. And we read into a buffer that also happens to be in this IPC message. So I think that was finished. And then okay. And then I was supposed to pass these 3 tests, and let's just check on how that is going. Grade lab 5. So I'm gonna comment these back, and I'm going to grade lab 5. Ooh. Grade lab 5. So now we are running tests. And this all succeeds. So I'm pretty confident we got exercise 5 working now. So now exercise 6. I think this was the part where we didn't finish last time. So so what is involved? Implement serve write in fs serve, that's the and dev file write. And then we should pass all the rest of these. So let's just take a quick visual inspection at serve write. it should follow a very similar pattern. We have this write request. We use what's inside to open the file. Then we just call the file write function. And then update the offset, something like this. That seemed pretty straightforward to me. The counterpart to that was this dev file write thing. And what is dev file write? So serve write lives over here. Dev file write probably lives over here. Serve write is on the file system server side. Dev file write is in the calling client code side in the client process. And these dev file functions are supposed to use this IPC channel to send an appropriate message over to the file system server. So let's take a look. Looking for, wow. Okay. File write. And then dev file. Okay, but file write. Okay. Okay, nice. So let's take a look. Wait, but no, I wanted serve write. Serve as C, serve write, okay. I think this is a fake compiler error for some reason. I think it actually did compile. Yeah, just make sure it compiled. Yep, it did. So okay, so file right. So what do we need to do? We receive file descriptor, buffer, and a size to write to the file. And what did I do? Okay, so let's look at some of the structures here. This IPC buffer. So when we fill out the message for the write request, we have this buffer, this structure to fill out, and we have a buffer for the actual data to send over to the file system server. And it has a particular size, and it's something like this, just the rest of the page, basically. So minus an int and the size t. And the client can give us a buffer of arbitrary size, but this is the maximum we can support in a single write, actually. So the first thing I do is I take the minimum, whichever is smaller, the size that they give or the size of our buffer. And that's the size we're going to use for the writes. So then I start filling out some of the information. I just put that into the size field. And then I use memmove. I use memmove because the other parts of the code do that. But I don't really know why it's memmove and not memcopy, actually. That was maybe I'll add a... Okay, so then I copy in the buffer into the request buffer from the given buffer for the amount, for the size amount. Which I think should be correct. And then I set this file ID thing. So I don't do that much. And then I trigger the IPC function. And what does the IPC function do? Even an FS, a type of FS IPC, because apparently there are different types. The type goes into the 32-bit number. So with an IPC message, you can pass a 32-bit integer and then an optional page mapping. Okay, I will be back 17 seconds. Okay, so FSN, what, static? Okay, this, interesting. The file system server is kind of special. Although, how does this work? I'm not familiar with this find env thing. Okay, anyway, not that important. We do an IPC send to the file system server with this type, and we pass in a pointer to the IPC buff, and we give it writable permissions for the shared memory mapping. And then we receive. And this does not require any mappings, I suppose. What is dest.va? I think I probably copied and pasted this code from somewhere else, like right here. So this was supposed to trigger the IPC. Okay, and that was my quick attempt. And it does not seem to be working. File write, because when I enable, let's just enable the first of these tests. And let me maybe disable the rest of these. Oops. So apparently there is an assertion error. Okay, so I guess it's time to do some debugging. Why is there an assertion error? It could be for many reasons. How would I even begin to debug this? So what does this test do? I don't even really understand these tests. Match test, test file. Wow. Runs a user's binary, maybe. So file write, test file.c. Okay, so what is this? This is a user program. And we succeeded until file write. This is file read, I guess. And this user program prints information, like prints some messages, and the test infrastructure looks for specific messages. Stale file ID. So all of that passed. File write is over here. What? Like I wish I could just run it and actually see what the assertion was, or I don't even know. I guess this is a Python assertion. There's some. Maybe can I get more information from the grading script? Help verbose. While I'm at it, I am going to comment out this stuff. Let's try this again. Maybe verbose mode helps. That did not help. Missing. So is this joss.out? I think that was produced by the test run. Let me run that one more time. I think that joss.out is what I need. Okay. Let's take a look at this joss.out file. That's kind of unfortunate that joss.out. That VS Code could not open it. Okay, kind of copy that into our workplace for today. User panic in FS in the block code cache. Dang. Sys page map invalid parameter. Breakpoint trap. Is that how user panics work? Okay, let's check out this BC. So this is our clue, bc.c105. Ooh, oops. So we're in here. What, how do I find the definition of this? Do I just dig grep? Here. In 3, this checks out. So this is how user space panics. And that's why we see a breakpoint trap, is because that's what it does. It does an int 3, which just triggers a trap and kills the process, I guess. Or maybe not even just kills the process. Yeah. Okay. BC 105. Flush block panicked. What is happening here? What does flush block do? Flush block flushes a block from the block cache to the disk. And it writes to disk. What is this? In BC page fault sysmap page blah. What did it say? Invalid parameter. Invalid parameter. I actually don't really even get what this is doing. I think it's passing 0 outer, 0 outer, which basically just means change the permissions on the virtual memory. Then clear the PTED bit using syspagemap. Did I do this? Also, did I write this code? I think I did, yeah. I'm not so sure. Flush block. I did write this code, yeah. So it's possible there's a bug here. But the interesting thing is this system call is panicking for some, or not, the system call is returning an error. An invalid parameter error. my guess is that we are hitting this like panic line. Yeah, and I'm just going to quickly test this by doing my own panic. And I'm running it again. Yeah, I'm just gonna run it. It'll clobber the file probably, but we already saved it. Or maybe not. I think this didn't change. This still says invalid parameter. There's quite a few reasons why this could have failed. I could debug it, although I'm a little bit unsure how best to do this. Or I could just try to think about this harder. Am I even doing this right? What I'm doing, int use the PT syscall constant when calling syspage The goal is to clear the PTED bit. What is PTED actually? PTED is the dirty bit, which is an officially used bit, an architecturally used bit. And the goal is to clear the dirty bit. I guess the dirty bit is how we tell if we really need to flush it, because if a write happened to it, then it gets marked dirty. We check. This is how we check this, right? We get the page table entry. And we mask it with this bit. And if it's not 0, that means the bit was set in the page table entry. Okay. So my understanding right now is that this should successfully clear the dirty bit if it is, wait a sec, adder aligned. I think I need to be using adder aligned here. So we receive an arbitrary address, then we align it down to the nearest page size. And we shouldn't actually really be using adder directly. I am fairly confident that's the bug. Oops. Try that one more time. Blind. Let's try that one more time. And it works. Okay, that was the bug. That was the bug. So... what I'm going to do is I'm just going to amend this into this commit where I implement flush block and where I introduce the bug. Okay, let's maybe that fixed a lot of things. Okay, so how many tests are we expected to pass? Large file. Okay. Okay, so things kind of worked. File write, read after write. Okay, large file did not work. Bad block number. So bad block number is 000 in disk adder. That's interesting. So that's coming from, again, from the block cache. Here. Block number 0 is not eligible to be used. Right. So somebody was trying to use block number 0. Who could that have been? So there's quite a few callers of disk adder, actually. But a lot of these are in check functions, so that's not production code. All right, another 20-second break to stand up and stretch. Be right back. So I'm just auditing all these places in the code. But maybe even before I do that, maybe I should actually look at what this large file thing is. So here we're making a large file. Which means a file that exceeds the space that can fit the indirect blocks, and it's big enough to require overflowing into the indirect blocks. It overflows the direct blocks, yeah. It overflows into the indirect blocks. It would be great to have a stack trace of who is doing this. But I don't really have any way of getting stack traces. At least, yeah, I never quite got that working. So doing some no stack trace debugging. I kind of think I can audit the code and get somewhere. There weren't that many real call sites. All of these were tests. And there's like a handful of actual call sites here. So what we're seeing is that somebody is passing in a bad block number into disk adder. So I think I'll just quickly try to audit all of these places in the code. Let me clear some space out. Okay. Starting, okay, these don't count here. So here we are in file block walk. So the idea here is that if the indirect block is 0, we fill it, and then we can proceed here and get its memory address after we allocate a block for it. So I'm not immediately seeing a problem with this. Although, wait a sec. Actually, no, I do. It's right here. Yeah, this is clear. This is the problem. At least that was a problem. File block. Where is this thing? fs.c. Walk. Okay, that was kind of a stupid bug. We allocate the block, and then I tried to memset it using the indirect, which is still 0. So the bug is that this thing should be higher, but really, I don't love that this ordering matters so critically. So maybe I will just use, oops, new indirect block number. So I can eliminate this ordering dependency. That otherwise it would be so critical that this needs to happen first. So that was a bug. Yeah. So now I'm clearing out the block correctly. And I passed all the tests. Nice. So I think that was, that's it for exercise 6. That's pretty cool. Now we're passing exercise 5 and 6, and we have more progress towards a working file system code. I'm curious if these tests test the offset stuff at all. So they do a bit of offset testing, I suppose. This is very interesting. Wow. They just check that it's not 0, though. I guess that's it. Okay. So just time to do, can delete this. So this is a bug fix. Which should go here. Right. Implement block walk. Okay, so now, right, this was exercise 5. But then, okay, then these were some improvements for exercise 5. So I will amend that into exercise 5. Serve read. And then exercise 6. But wait a sec. Where did, oops, Where did my dev file write changes go? What? WK. Oh, damn. I think I accidentally amended these changes into the wrong commit. Let me fix that. So I need to, yeah, it's these changes are not in the right commit. So let me just move these into the index. Okay, so now this is better. So now I have these changes, but I don't actually need any of this stuff. Furthermore, I can even delete this stuff. So now we have the code for exercise 6. Cool. That's awesome. I'm pretty stoked. Let's keep it moving. Well, let me get some. Let's take a quick sip of water. Be right back. So lab 5 is going pretty well, actually. I guess there's 10 exercises, but we are blazing through the file system. Okay, spawning processes. We've given you the code for spawn, which creates a new environment, loads a program image from the file system into it, then starts the child environment running this program. The parent continues independently of the child. The spawn function effectively acts like a fork in Unix, followed by an immediate exec. We've implemented spawn rather than a Unix exec because spawn is easier to implement from user space in exokernel fashion without extra help. Think about what you would have to do to implement exec in user space and be sure you understand why it's harder. Okay, let me see if I understand that. Unix style exec. So what does this even mean? So first of all, yeah, what do these two things even mean? Spawn versus exec. So what is a Unix exec? Unix exec system call takes a process and you can specify and you pass it a file system path, which it executes and basically destroys the current process, and the new program completely takes over the execution of the process, I believe. But actually, now that I think about it, there's a lot of details I am not familiar with, like questions I have, like I guess my understanding is that all resources of the previous program get destroyed, including any threads and stuff like this. Release all resources of the old process. Threads, files, scriptors, memory. That's my understanding of what exec is. So, and spawn. This function is basically like a fork and immediate exec. So we have fork in our OS, but it's in user space. But what you have to do to implement exec in user space. So that's sort of the alternative. Option number one is spawn. Option number two is fork and exec, also in user space. And they're claiming that it's easier to implement spawn than to do this. Maybe this answer will be clearer to me after I actually implement spawn. Without special help from the kernel. I'm going to revisit this question after I do the exercise, I think. Okay. Clear out some of these old files. Lib spawn. Let's check out what spawn does. Also in user space. So this is like a libc function sort of thing. Spawn a child process from a program image loaded from the file system. You give it a path and then some argument strings. So when you call this, it doesn't destroy your program, your process like an exec would. It creates a new environment and just starts running this independently of the child. What does this independently mean? Do these things have a parent-child relationship? Oops. When you fork, that, like, the answer is yes. But I'm not quite sure with spawn. Maybe not. Like why would it? You know, actually, I mean, that's even a question within fork and exec. That's like a very, very basic OS kind of question. I mean, I think they do, because with fork and exec, you can still share file descriptors between the parent and the child. I mean, actually, this is like kind of an ultra basic question to be asking, but I mean, yeah, I'm pretty sure you still have a parent-child relationship. So how does this work? So what does this need to do? You give it a program path, and it needs to load a file from disk into memory. So we need to make a new process also. Load the file from disk, load the ELF binary into the process at the appropriate mappings. Sanity check the ELF. Create a new environment. Create an initial trap frame for the child. Init stack. Map all of the program's segments into the new environment's address space. So load the ELF basically. "20 seconds, stand up and stretch, be right back." So if the flags are not writable and the segment contains text and read-only data, use readmap to read the contents, then map the pages it returns directly into the child, so multiple instances of the same program will share the same copy of the program text. Be sure to map the program text read-only in the child. Read map is like read, but returns a pointer to the data in the block cache rather than copying the data into another buffer. So that's interesting. So we load the file from disk into the block cache, which is like memory. And then we just simply point back to it. We don't copy it again into like another allocation. So if the flag does have writable, then the segment contains read-write data and BSS. BSS is like the zero region, right? Which we need to mem set to 0. That's the 0 data, right? That's like an init.c. The first thing we do is clear the BSS uninitialized global data, which is 0 initialized. But why? But is it always writable though? I guess otherwise it would have to be a constant 0. Okay. Only the first. As with load I code in lab 3, such an ELF segment occupies p mem size bytes memory, but only the first file size bytes of the segment are actually loaded. You must clear the rest to 0. For each page to be mapped for a read-write segment, allocate a page, temporarily read the appropriate portion of the file into that page, and or use memset to 0 the non-loaded portion. Then insert the page mapping into the child. Be sure you understand why you can't use read map here. Okay, I can screenshot of that just to remember it. None of the segment addresses or lengths above are guaranteed to be page aligned, so you must deal with these non-page aligned values appropriately. The Elfinger does guarantee that no two segments will overlap on the same page. It guarantees that page offset. Page VA, page offset. Okay, I don't remember those fields well enough. Call sysenv set trap frame to set up the correct initial EIP and ESP values in the child. Okay. Start the child process running. Okay, so that's basically how load and execute a new program. So for context, in the history of this OS, first, we didn't have any user space. The kernel just like booted. Then we were able to kind of like hard code some user programs into the kernel, which the kernel will then use as the init process. But then these init process, like these users, like the first user space process, we didn't have fork or anything, so there wasn't any dynamic behavior, like processes could not create new processes. So then we implemented fork, and then processes could create children and do stuff with them, and wait on them, I suppose. I forget. And now we're going one step further, and we're allowing, not only can processes fork themselves, but they can also load other programs from disk. Because now we have a disk. Okay. So let's just quickly take a browse through this code. Open. So this is also kind of new to me. I haven't seen all this code yet. This is like the open column libc. It takes a path and a mode. Check the path length. Allocate an FD. So this is new to me. So how does this work? And also, why is it so difficult to find these definitions? Okay, this is totally foreign code to me. Without going too deep. So we allocate a file descriptor. Copy the path into this request thing, and then I do an IPC open. Interesting. Which might fail, otherwise returns us a file descriptor. fd2 num. It returns us So does fd_alloc this thing doesn't really allocate memory, but it does set a pointer index to fd. Fd table, wow. So there is a section of memory for file descriptors or something like this. And apparently each file descriptor gets its own page. So it's able to do this. The caller. Do you need to allocate a page? Huh. Okay, yeah. It's totally foreign code. No idea. I've never seen this before ever. But this is an open request. Anyway, so we can open and get a file descriptor out. And then we can use, so our elf is limited to what, 512 bytes or something like that? And we just fail. We try to read the 512 elf. And if we weren't able to read the whole thing, or the magic didn't match, we fail. Interesting. So now we have our 512 byte elf file, which seems kind of small. And this, read n is just a wrapper over read. Okay. And it's just a read wrapper that retries until the whole thing succeeds, basically, or like actually fails. But if there's a partial read, it retries to make up the difference. Then we create a new child. Set up. What is child TF? Trap frame, and it's an actual trap frame. We make a copy. env-x. I wish I knew what this did, but you pass it an env ID and it offset. It seems like it just kind of masks off any high bits that are too high. Or okay. Environment index. Uniquifier. Okay, so the uniquifier is like a nonce. Interesting. So then we look up a trap frame. And set the entry point. But like what? I kind of don't get. Do we need to completely repopulate this state of this thing? I think we kind of do. I think we do. The other thing I'm thinking is like, why do we need to do it this way? Why can't we just create a plain trap frame and then fill it out? Why do we need to make a copy of it like this? Because doesn't this have like remnants from maybe a prior process or something? So that's confusing. But anyway, we just start filling out the trap frame. We init the stack. which requires what? Mapping memory in the child. Based off of the given arguments and stuff. There's quite a lot of code actually, yeah. Count the space used by all the arguments. Determine where to place things. So we allocate, so first like we use utemp and write a bunch of stuff, and then at the very end we like map it actually into the child. Right, again, the context this code is running in is it's running in the parent, which is calling this libc function. And then it kind of transfers ownership of that page into the child. Copying string data. And then it also takes an output parameter of where the ESP needs to start at. Which gets set into the trap frame. And then we load the elf file. Oh, I guess, okay, so this 512 byte buffer is just for the header, I guess. And then this map segment does more IO, maybe, or no? For every program header, map segment. This page alloc. Seek read and yeah, so we do more file IO based off of, for example, the file offset. Yeah. It's like hard to read. Okay. Allocates utemp memory, reads into it, and then maps it in the correct way. So there's this general pattern of using utemp and then as a working memory buffer, and then mapping that into the child. We allocate a new page, map it at utemp, do some stuff, and then map it where it needs to go ultimately, and release ownership from the parent. From the parent. So now we're apparently done with the file. Copy shared pages. Interesting. And apparently I need to do something here. Okay. But I'm like going kind of deep into this whole spawn thing. which is later, right? So that's, I think I'm getting a bit ahead of myself. Okay. Spawning processes. So let me just go back and do the exercise. Spawn relies on the new system call sysenv set trap frame to initialize the state of the newly created environment. Implement sysenv set trap frame in kernel syscall cdom for dispatch. Test your code by running the user/spawn hello program, which will attempt to spawn /hello from the file system. Cool. Okay. So, and this is actually the call site. So after we do stuff, we're trying to set the trap frame of another process, basically. Why does this say devious? Okay. 20-second break to stand up and stretch and be right back. So we're a process. We created a new process and are filling it and getting it ready, populating its memory regions, setting its register state that it will use. Okay. But actually what we've done is we've just been populating our local copy of the register state. We need to actually write that into the kernel's notion of the register state. And we need a syscall for that, apparently. So that's what this is all about. Set env-id's trap frame to TF. Make sure TF is modified to make sure that user environments always run at code level 3 with interrupts enabled. Okay. So we are passed a env-id and a pointer to a trap frame that user space has provided. So we do our typical thing of it's either user mem assert or user mem check. Which one? I always forget which one is the actual, like, I think assert is like the higher level function. Check that environment env is allowed to access some memory range with some permissions. And if it cannot, env is destroyed. And if env is the current, this will not return. Okay. So user mem assert env-id trap TF size of TF with perm okay, so what is up with this? What permissions are we trying to access this memory with? In this case, we're just reading a trap frame from user space. Unlike other system calls where the kernel is actually writing to the pointer provided. In this case, it's just reading. So I'm just gonna pass 0 because I think it already takes care of passing all the correct things, but I'm curious what the other call sites of this use. PTEU, I guess. PTE write is actually used here. because we're actually about to write into user space. This is part of the user space interrupt handling. So in this case, I'm just gonna do PTEU, just to not put a confusing 0 there. Okay. So we first validate this pointer that user space has given us. And then env to d, env id, env true, check perm. It's error equals just env id t env equals null. If error, return error, something like this. And now we have an environment, and so I think this is wrong. Env struct env. I think that's the type. Something like this. We copy. Yeah. TF is modified to make sure. All right, TF. So then, we load their TF, but then we tweak it so that the code protection level is always level 3. And interrupts enabled. I know how to do the second one, I think. Wait, TF E flags or equals flags interrupts. I did this before. Where I'm just going to grab FLIF. That's the way we do this. And apparently, I don't know why this says devious, but FLIOPL, or maybe that's not, or maybe it's also right here. So this is a little bit poor form with the way I am. Okay, no, I need both of these. Wait a sec. No, this is about the I/O. No, this is actually totally wrong what I just did. That's only for the file system server. This is totally not right. What I need to do is find out which bits in E flags correspond to the privilege level. Which is not I/O privilege level. But wait, do any? To make sure user environments always run at code privilege level 3 with interrupts enabled. Okay, so I not sure. I'm also kind of wondering what's the difference between interrupt flag and trap flag? Let me get my chat GPT. Here, 1 second. Okay. Before I ask this, I'm just going to, so I know the interrupt flag is just, are interrupts enabled on the system, but what is the trap flag again? Maskable hardware interrupts. Enable single step debugging mode. That is so obscure based off of the name. Okay. Okay, it's like a debug thing. Okay. But wait a sec. Okay, so the interrupts enabled is always run at code privilege level 3. What governs this again? I'm like kind of blanking on that actually. I thought it was the trap. Wait, no, it's not. Oh yeah, so it's not in the flags. There's something else in the trap frame that might be relevant. CS, maybe. I think it might be this thing. Yeah, wow, that's quite the detail. So, yeah, there's a segment selector that controls this. So technically, I think it's like actually like a lot of this, but I'm just thinking from kind of like a security and protection point of view, what is happening here? So I'm just going to sketch it out. So we have a parent process with a child process, and then we have the kernel. And there's this line between them. And the parent process creates the child using a system call and does a bunch of stuff with system calls, and then is creating this trap frame, which is going to contain the initial states of the child's registers. But the kernel needs to be the one to eventually know about this. The trap frame is stored so the kernel has internal data structures for the parent and child for these environments. And part of what's in these is the trap frame for each of them. So when the kernel chooses who's going to run, it uses the trap frame to set the registers. And so what the parent wants to do is construct this over locally in user space, set a bunch of values, then pass this to the kernel and say, hey, please, when the child starts, use this data to initialize it. And I see, now I understand what was happening here now, because, okay, so there was a dependency between this and the sysexo fork, which actually allocates a child environment and populates a lot of these initial values, basically. That's the part I was missing. Okay. Yeah, and so we allocate the environment, and then we assume and expect that this populates, or basically constructs the environment like object. So then we take this kind of constructed object and we customize it a little bit. But the thing is, the malicious, like some kind of malicious parent is at liberty to basically change anything about this. So really the kernel should be validating this quite carefully and only permitting like very select changes to the trap frame, technically speaking. And that's part of what this exercise is all about. If I can find where I even was again, which was spawn.c. Or rather, no, I was in the system call, yeah. Here. So now we're receiving this thing that the kernel, that user space has passed to us. And we could just blindly put it there, but then the kernel, but then the parent process, if it was malicious, could set all sorts of other random stuff and change so many things about the trap frame. For example, to allow the child to execute with kernel privileges or something like this, which we generally want to avoid. So that's why it's saying modify TF to make sure code always runs, in the correct state. Basically ensure that all this important stuff is retained. Which would basically mean set everything, because the child environment could do anything it wants. Maybe another way to do this would be to require user space to pass specific things for the trap frame, rather than just like a whole trap frame, which exposes a lot of internal details. So the main thing it's talking about are these two things. Make sure that the segment selectors are all set to user space. Yeah. And then also, but like there's also all this random stuff that shouldn't really be messed with. It's actually quite powerful if user space can completely control a trap frame for a process. So if I were doing this for real, I think the appropriate thing to do would be to extract a lot of this code out into a helper function that initializes one of these structures. And then basically just call that again here to force correct any Yeah, like any of these members that may have been changed, such as these, for example. I'm going to not do that for the moment because I'm just trying to move quickly with this. Oh. Wow. Vim skills, okay. I'm just going to do this for now. So we take their trap frame, copy it into ours, patch a bunch of stuff on top of it. Yep. And then return 0. That's my, and then we need to dispatch this system call. Switch, okay. This will go down here, I suppose. Case sys set trap frame. Break ret equals sys set trap frame. And it takes 2 arguments. Does this build? No. Oh, what? The first... Okay. The first argument is an environment. So I need to call this here, actually. Pass an env. This build. No. Okay, then I need to correct this. And that builds. 20-second break, be right back. Okay, so let's try this. And the way it says to try this is to run user spawn hello from kinit. Env create. This is what. I'm just going to try doing it this way. User spawn hello. Does this work? It's been so long since I've. Is this how you run stuff? Did that work? It says hello world. Spawn hello does what? I'm parent environment blah. Spawn hello hello. Which passes in an argument, okay. And then we go to hello.c and it says hello world, I'm environment blah blah blah. And that's exactly what we see here. So I'm gonna say that worked, which means I successfully did exercise 7. It says use make grade to test your code. Let's run it. Oops. And it worked. That's awesome. So I will just finish off. I'm not going to commit this, but I will commit this. Let's clean this up a little bit. Let's see. Okay. Okay. Okay, so I'm gonna do this, commit, exercise 7. Okay. Challenge, implement Unix style exec. Yeah. All right, cool. Yeah, that's gonna be it for right now. I'm pre-recording this stream, and in a little bit, I'll be doing the next stream live, which will be exercise 8 and whatever all this stuff is. Cool, thanks a lot for watching. I do this every week. Please subscribe if you like the content, and I'll see you in another one. Peace.